Hello and welcome to our project presentation for the Network Softwarization courses, the Principles and Foundations and Technologies and Enablers course. Our project is for online traffic identification. For online traffic identification, the goal is to be able to identify the type of application that a flow represents using the first few packets of that flow. So this is useful for modern networks in optimizing the operations of the networks and providing other services such as capacity planning, traffic engineering, and anomaly detection. So there are traditional techniques that are being used for identifying the network traffic. Those techniques can be divided into three main categories: port-based techniques, payload-based techniques, and behavioral-based techniques. For the port-based techniques, the traffic classifiers look at the port numbers of the packets, and using the port numbers they identify the type of service within that flow. However, the problem with this is that modern applications use dynamic port assignment where they change the port numbers within the same flow, and that makes it challenging for the algorithms to identify the type of applications just by looking at the port number. The payload-based technique conducts deep packet inspection by looking at the payload of the packet in order to identify the type of application within that flow. And the drawback of this is that deep packet inspection can be illegal in some locations, as well as the encryption being used by modern applications to encrypt their data within the payload of the packet. The behavioral technique leverages the use of statistical learning using supervised or unsupervised machine learning models to infer the type of application or the class of application a flow belongs to. And the problem with this is that each flow would need to be translated into a set of features that are understood by the learning model in order to conduct classification. Some of those features can be computationally expensive to calculate. So our project focuses on the last category, which is the behavioral learning. So for this we need a data set in order to train our machine learning models and test their accuracy on generalization performance. So for this project we were given a set of packet capture files that include packets captured on two different networks, the information, so destination IP addresses, the layer 4 port numbers, and packet length, and more. So we were also provided with ground truth files which provide the labels for the applications that each flow belongs to, and these files combined with the packet capture files would enable us to create a data set labeled with the application type for training supervised machine learning models. So for the labels, using both the ground truth files and packet capture files, we design our data set. So each sample in the data set represents a flow, and a flow is represented by a group of packets that share the same source IP address, destination IP address, source port number, destination port number, and layer 4 protocol. As for the labels, different applications were classified into 6 main classes. As you can see on this slide, mainly web applications were assigned to class applications, class 1, etc. So for each flow or sample point in our data set, it will belong to one of these 6 classes, which will be the label of that sample point. Having a flow and a label does not complete our tasks for preparing our dataset for machine learning models. We need to generate features, and feature generation is the method of representing the data sample, or in our case flow, in terms of a set of features. And the set of features can be changed, and new features can be added, features can be combined, which is usually referred to as feature engineering. And the set of features being used to train the machine learning models do impact the performance of these models in terms of accuracy and general performance in terms of time. So we create 3 initial feature sets that we use in our training models. The first set involves that were created using functions that were provided and studied in one of the NetSoft data analysis labs. Those features include features related to the inter-arrival time between packets of a certain flow, the length of mean length of the packets of a certain flow, the number of retransmission within a certain flow, and others, as you can see on this slide. So 4 of those 28 features generated were found to have the same value for all the different samples, so they were dropped and we were left with 24 features. The second representation feature set included the 24 features that we discussed, and in addition to 6 new features. The 6 new features were meant to provide information about the interflow correlation, or the relationship or the correlation between the different data samples in our data set. So these features were generated by means of an unsupervised machine learning model that was used to cluster the original data set into 6 different clusters corresponding to our 6 classes. And the 6 new features represent for each flow represent the distance of that flow or that data sample to the centroid of each one of those clusters generated by the k-means clustering algorithm. We'll explain that further in a following slide. A third representation, we just included the 6 distance features. So for interflow correlation, let's explain it further. So interflow correlation describes the similarities between the data samples in a data set, and in this case each sample corresponds to a certain flow. So the interflow correlation would show the similarities between the flows of different classes and the flows among the same class. The reason why we wanted to use features that encode information about the correlation between flows is that machine learning models that conduct the task of traffic flow identification exhibit poor performance when the number of packets that are used to identify the flow are very few, 5 or less, and that's the case with the mice flow, which are network traffic flows that are composed of a limited number of packets. For our project, we represented the 6 features in one of our data sets to encode the interflow correlation information. And in this case, we used the k-means clustering algorithms to cluster the full dataset into 6 different clusters. Those clusters, the reason why we chose 6 is that it corresponds to the number of classes we have in our labels. And for each sample, we created a 6 value vector. Each value represents the distance between that sample point and the class center in the 6-dimensional space. And by doing this, we can use that 6-dimension vector to compare or compute the correlation between two different samples in our 6-dimensional space, and by this we get information about the correlation or the similarity between those two flows. For instance, from like we observed by using the information of the interflow correlation, that class 0 flows, or the flows that belong to class 0 and the flows that belong to class 1, tend to be very close to each other in that 6-dimensional space, which shows that these classes have flows that are similar in their distribution, and they're probably they're probably hard to separate, and it will be difficult for machine learning models to classify them correctly, because you can get a lot of false positive from one class to the other, given how those two classes are close to each other in terms of the nature of their flows. Class 2 is the most distinct and different class, so in this case, when it's compared to other classes, it will be easy to classify it as class 2 or not class 2, as opposed to the case with class 0 and class 1, where you could be confused by the classifier. So we move further into quantifying this interflow correlation between flows of the same class and flows of different classes, and in doing so we calculate the variance within of the flows within the same class, and we can see that the variance in class 0 and class 1 is relatively low, so the flows of those classes are similar. Like the flows of class 1 tend to have similar characteristics to each other. This is not the case with the class 2 flows and class 3 flows that have high variance, and this shows that you can have two that belong to class 3 but have different characteristics. So our data set that we just described and feature set poses certain challenges that have been identified in the machine learning literature, and in the next few slides we'll identify these challenges and show how we develop techniques or use the techniques that enable us to combat them. So the first challenge was the dataset class imbalance. If we look at the 6 classes that we have, we would find that we have a lot of data samples or flows that belong to class 0. Almost more than 50% of the full data set are flows that belong to class 0, as opposed to flows or data samples that belong to class 5, which are very few. And the data set imbalance poses a problem in terms of if you're trying to train a machine learning model using an imbalanced data set, you're showing it too many examples of one class but not enough examples of the underrepresented class, so it ends up knowing or learning more about the highly represented class, and would end up being skewed or biased toward classifying new samples, like samples that data that it hasn't seen before, towards that class that it has seen more examples of, while misclassifying the classes that are underrepresented. So there are ways to balance the data set. So the most traditional way is to limit the number of flows that you use from each class in your data set to the minimum number of flows in the least represented class. However, this results in inefficient use of the data available. Like you would have a lot of data available to train for class 0, but you're only using like a tiny portion of it in order to maintain the balance with class 5, which is underrepresented. So this doesn't allow our machine learning models to develop complex hypotheses that might be needed in order to separate the data that we have. And it also does not allow us to be free with our feature selection, and imposes the need for feature reduction in order to adapt to the few data samples that we have. So because the more features the more features you have, or the more model parameters you have representing your data samples, the more samples you will need for training the machine learning model. Another issue facing us is the curse of dimensionality. We looked at the 3 different feature sets that we have, and they 2 of them had 20 features more, and these are relatively high dimensional data samples, and so higher dimensional data sets would require a more complex hypothesis or a more complex model to separate them in that high dimensional space. But the complex models generate hypotheses that tend to overfit the data and show poor generalization performance. Another challenge that you would face with high dimensional data is that model training time. So model training time, there are different factors that affect it, mainly the complexity of the machine learning model and the hypothesis that it's producing, as well as the number of features and the number of samples you are using to train the model. But it becomes essential to maintain a low training time in applications similar to network traffic identification, where you're constantly reintroducing new samples to the network, or new flows to the network that would need to be used in retraining the model in order to maintain its performance and accuracy. So the remedy for most of these challenges that we mentioned above is dimensionality reduction techniques. And dimensionality reduction techniques look at ways to reduce the number of features represented each sample in the dataset, or in our case each flow in the dataset. So less number of features allow the not very complex models, such as support vector machines, that produce linear hypotheses or like simpler hypotheses that do not overfit the data, so they allow these models to perform well. You cannot use these models with high dimensional data sets, by reducing the number of dimensions, you open the ability to use or leverage the use of simpler models that are not prone to overfitting. And it also improves the training time, as you have less features mean less model parameters to tune in order to or to train in order to achieve convergence. In our project, we investigated the use of unsupervised machine learning models in the network identification or classification problem, and unsupervised machine learning models do not require the labels that we have in our data set, so they're usually used, as we mentioned, the k-means clustering algorithms for clustering unlabeled data by looking at the inter-data correlations or the similarities between the data samples. We use unsupervised machine learning model here to investigate the suitability of unsupervised machine learning model in classifying our data sets. So Gaussian mixture models are a good example of an unsupervised machine learning model that has a probabilistic aspect to it, and it basically assumes that every sample in the data set comes from a distribution that can be generated using a number of Gaussian distributions with different parameters, and knowing these parameters that generate, for the Gaussians that generate each data sample, is what the Gaussian mixture model does or learns. So it's usually used for clustering, same as the k-means. However, in this case, we are leveraging the fact that we have the labels in our data set to initialize the cluster means with the means of these labels, and in this way we're able to see how efficient a Gaussian mixture model and unsupervised learning model would be in classifying our given data set into 6 distinct clusters. And the reason why we're choosing 6 is that we know from our labels that we only have 6 classes. So we're trying to see whether our data set actually fits within 6 clusters that are distinct enough for us to be able to separate them. And in doing so, we found that the Gaussian mixture model achieved a classification accuracy of 71.6% in classifying our data set into the 6 clusters when we fit it on the 4-component PCA or principal component analysis transformation of the 24 features. And we'll talk more about the PCA soon. However, it's like a feature reduction technique that reduced this our data the representation of each sample from 24 features to 4 features, and that actually provided better accuracy or clustering accuracy for the GMM model than when using the full 24 features, which also shows how feature reduction techniques are important for improving machine learning model accuracy and performance. So as we can see in this graph, it plots the number of components, or the number of PCA reduction components, and the accuracy obtained by clustering our dataset into 6 different clusters. And we see that we have better accuracies when we reduce the features of our 24 feature dataset into different or less dimensional PCA components. Given the interflow correlation discussion, as well as seeing how PCA can not only summarize the data set or the data sample into fewer features, we were intrigued or motivated to try and visualize the 3-component PCA of each class in our data set in 3D space, and that will give us some sort of intuition about the spread and the variance of each of the flows of each sample in each class. So we used PCA, principal components analysis, for dimensionality reduction to reduce the dimension to 3 dimensions, basically the 3-component PCA representation of the 24 feature data set, and that gave us the ability to plot each data sample in 3D space. As we mentioned, the PCA is one of the most broadly used unsupervised algorithms for dimensionality reduction, and is also used for visualization and noise elimination from a data set. So we can see from this graph here, we can see in this graph here, that's the plot of the 3-component PCA transformation of our classes. So each class is represented in a different color, and the points that have the same colors are basically flows belonging to the same class. And we can see that class 3, the blue, the light blue color, has a bigger spread, or like a higher spread than other classes. I think 2 and 3 have higher spread than class 0, given keep in mind that we have more samples representing certain classes than others. So, but you can kind of get a hint about the spread of the flows of a certain class, and it when closely investigated using the k-means clustering and variances of the 6-feature vector, we can actually see that the results go well with our observation here in this visual representation. We went a step further and used kernel PCA, which is another version of PCA that is that achieves nonlinear dimensionality reduction through the use of kernels, and we reduced our 24 feature dataset into its 3-component kernel PCA, and in order to visualize that in 3 dimensions. And the good thing about kernel PCA is that it's able to project the data set in a way that makes it linearly separable in that dimension, and we'll see that in the following graph. However, we found out that transforming the data set, or a data set with multiple features, to its kernel PCA components is very computationally expensive, so it's not practical to be used, and that's part of what we were mentioning as a drawback of the behavioral techniques for network traffic identification, where the feature generation and computation becomes too expensive to be practical. So in this, we can see that the component kernel PCA visualization of each sample in our data set, and different classes have different colors, and we can see that it does actually linearly separate the classes in 3D space. So that could enable us to use SVMs and simple linear hypotheses to separate the data. However, the limitation is in the computation of the PCA components. So that's with unsupervised learning for investigation and analysis. The main algorithms that we implemented for identifying the traffic and improving the accuracy of online network traffic identification were supervised models. So if we look at supervised models, we need to use the labels, and we need to separate our data set into different sections to be used for training, and others to be used for model hyperparameter tuning, and others to estimate the generalization performance of the model after it's trained by feeding in samples that it has not seen before. So this is known as train, test, and validation sets. So for our purposes, we divided our data set into 10% of the full data set as a holdout set to be used for validation after the model is completely trained and tuned, and the remaining 90% were split into 80-20 random split, for 80% for training and 20% for testing. And we use the classification accuracy of the model on the holdout set, on the 10% holdout set, as the metric for evaluating whether the model performance is well or not. It's a decent metric for evaluating the generalization of the model. However, it's not the best, it's not thorough enough. There are other validation techniques such as k-fold cross validation that could be implemented in the future to understand the generalization performance of these models that we present in the next few slides. So we tried multi-class classifiers that leverage the use of bagged decision trees, and bagging is an ensemble machine learning technique that combines weak classifiers to generate a stronger classifier, and we have seen from the lab that it provided the best prediction or classification performance among the other ones that we trialed, such as SVM and multi-layer perceptrons. So decision trees are the base classifiers used in the bagging technique here, and they're good for combating overfitting by reducing the chance of variance and providing a hypothesis set that has low variance. So the following slides will present the results obtained from the multi-class classifier that we trained using bagging, and we can see as we mentioned before, in order to balance the data set to be suitable for a multi-class classifier, we had to limit the number of flows that we are using for training the model from each class to 156 flows, which is the the number of flows that are actually present in our original dataset for class 5, the least represented class. And that shows you how much data we lost or we did not use from classes 0 up to 3, because we just throw them out in order to balance the data set. So if you're training a multi-class classifier, that was one of the limitations, and so now we will discuss the results that and in terms of model prediction accuracy and the training time of the supervised multi-class classifier using bag decision trees. We trained the model on different feature sets that we created earlier. Looking at the 24 feature set, our multi-class classifier obtained almost the same F1 score, which is a measure of performance or classification performance of the multi-class classifier. When trained on the full 24 features, as well as on only the 13 component PCA representation of those 24 features. However, the training time was significantly reduced when the 13 component PCA representation was used, and that shows you that the feature reduction techniques do improve a model's overall performance by decreasing the training time without compromising the accuracy. Looking at training the multi-class classifier using the 30 feature set, which had the 24 features plus the 6 distance features that represent interflow correlation, we also see a similar pattern. So here the reduction in training time is more dramatic. As we can see, it took 20 seconds to train the model using the full 30 features, and only 1.5 seconds to train it using the 10 component PCA representation of those 30 features, and the accuracy or the F1 score is almost the same. When we just use the distance features, which are the interflow correlation features, so those are 6 features, we obtained, as expected, the lower F1 score due to the limitation in the number of model parameters, which result in a limitation in the hypotheses that the model produces. However, we can also see the benefit of using PCA even at low dimensional feature sets, where we reduce the training time when training the model using the 3 component PCA representation of the 6 features. So one of the problems that we discussed with multi-class classifiers is that when in order to achieve balancing of the data set, you are of useful data for the overrepresented classes and limited by the number of samples available in the underrepresented classes in your data set. So one of the ways we thought about improving the performance of the multi-class classifier by having a different way to address the data imbalance is to implement 6 different one versus all or binary classifiers. Basically a binary classifier for each class that would where we feed it the data set labeled as its own class samples labeled with the right label, and all samples from all other classes labeled with the same label, which is a different label. So you implement 6 binary class or one versus all, as they're called, classifiers, and in order to achieve the class classifier, you feed the data sample through a pipeline of those 6 classifiers in series, and by the way we evaluated the performance of these 6 classifiers as one single multi-class classifier is through generating a probabilistic estimate of from each one of those classifiers of whether the sample belongs to the one class or the all class, and by looking at the highest probability for among all the 5 classes, we
deduce that the classifier classifies this sample to belong to that specific class. And this was based on studies that showed that one versus all binary classifiers when tuned correctly, and that also gives us the flexibility to tune each one of the binary classifiers separately to achieve best performance given the amount of data available for that specific class, without underusing any available data samples for any of the classes. So these studies have shown that you can achieve the same classification performance as multi-class classification problems. So we saw the benefit of this in cases where we have a heavily imbalanced data set that the one we have. So these are the results from when training the multi-class classifier, and we only evaluated it on the holdout validation set. That's why you see one curve. However, you can see the accuracy. In this case, it's an accuracy measurement a little different than the F1 score measurement, given the way the pipeline method that we're using to evaluate or to classify the samples of the holdout set. And you can see the same pattern in terms of reduction in the training time when using a PCA, a reduced PCA component representation of the original features. However, you can see that the accuracy levels are much higher than the ones obtained when training the multi-class classifier, the single multi-class classifier, but the caveat here is that the training times are significantly higher than those of the single multi-class classifier. When running the same model on the 30 feature data set, we can see a similar pattern, and again we can see a reduction in the training time when applying PCA feature reduction. Similar to the 6 feature data set, the distance features, and we can also see that this feature set provides less accuracy than using the higher dimensional feature sets, which shows you that while dimensionality reduction could be useful, it can also hurt the efficiency of the model by not giving it enough high parameters to tune, or model parameters to fit like a more complex hypothesis. So in conclusion, we conclude that PCA feature reduction can improve the training time of supervised machine learning models without compromising the accuracy. So feature reduction techniques are useful, and PCA is one of the most common ones used for data visualization, for like we saw here, improving the training time and like summarizing the information of many of high dimensional data into fewer dimensions that are easier to work with. We've also concluded or investigated that unsupervised models are very helpful in examining the distribution of the data samples, or in this case and of our flows, and they can give us means to generate or engineer new features that in this case we used the interflow correlation features in training the model, and while we could not attest that the additional features improved the model over the original 24 features, however we can see that there's like usefulness when we go to a further in different classifiers and different models. We also conclude that the class imbalance problem is a common issue with network traffic datasets, as the same with the case as mice and elephant flows. As we saw here, most of the samples that we had were web data, while we had very few of class 5. So that's something that has to be like addressed in terms of dealing with network traffic dataset. And the trade-off between the training time and the model accuracy and that's probably more important in terms of network traffic classifiers than other machine learning applications, given the fact that the models that will be implemented in industry would require constant retraining on new data sets and new samples or new flows that are coming through the network. Thank you very much for listening to our presentation, and thank you.